Algebra 1, though, was easy because they were all written conveniently, so you didn't need logs in Algebra 1 because you never learned about them yet. So everything in Algebra 1, and still sometimes you'll come across them, is written in such a way that you can get the same base on both sides. So the big property at the top is if you have the same base and one side is raised to the m power and the other side is raised to the n power, then those two powers have to be equal to each other. You essentially can just drop your base. So if you look at number 1, the base of 2 and the base of 16 are different, but they can, like 16 can be rewritten differently. So 2 to the 3x minus 8 equals 2 to the 4th power, just replacing 16. So trying to create that same base on both sides. Once you have it, it cancels. So you're just really solving 3x minus 8 equals 4, adding 8 to both sides. And getting your answer. Okay, so if it's possible to get the same base, that would probably be your go-to option. On number 2, you have a base of 27 and a 9. Can they be written with a common base of 3? This is a little bit harder than the last one because 16 just became 2 to the 4th and there was nothing else to it. 27 is going to become 3 to the 3rd, but that's still being raised to the x plus 3. So now you got to sharpen your exponent rules a little bit. When you raise a power to a power, you multiply. And when you multiply a monomial times a binomial, you have to distribute. So that becomes 3x plus 9. Does that make sense, everybody? On the right side, 9 is 3 squared. $27 is 9 to what power, though, in your head? Right. Yeah. There are sometimes multiple options, but this wouldn't be one of them. So 3 squared to the x minus 1 becomes 3 to what power, Carolina? Correct. Good. So you just distributed that. Now that your 3's are the bases and they're the same on both sides by themselves, cross them out and just solve this equation. 3x plus 9 equals 2x minus 2. Subtract your 2x over. Subtract your 9 over. You get x equals negative 11. Jump to 5, because 3 is going to be like number 1. 4 is going to be like number 2 just was. 5's a little bit trickier. The base is 1/3 on the left and the base is 9 on the right. They both can be written with a base of 3. But this one's trickier because 1/3 is 3 to what power? Negative 1. So that's, if you see a fraction, it's typically going to tap into a negative exponent. And then 9 is just 3 squared. So when you multiply those exponents, you're going to get 3 to the negative x minus 3 and 3 to the 2x. And your 3's cancel. Get all your x's on the right, so add x. Divide by 3, x equals negative 1. Yep. So, I think, I'm trying to think, they'll all be 1 over something. So 1 over 9 is like 1 over 3 squared. which would just be 3 to the negative second. So whatever the power of that is, that's just a negative exponent. And usually you don't want negative exponents. We actually, when we're simplifying, we're trying to get rid of them. But when you're trying to get common bases, you actually create the negative exponent so that you do have the same base on both sides. So if I did 1 over, I don't know, 64, that would be 1 over, oh boy, 2 to the 6. Or 4 cubed, if you wanted it to be a 4. And that would be 2 to the negative 6. Good? Anything else? The last one, number 6, is same idea, a little bit more complicated just because the base is E, number 1. And number 2, on the right-hand side, we've got a little more to do. The left-hand side is all good, right? Base is E. There's nothing to do with that. The right-hand side, Sarah, what happens to this? 2x times, and what happens to this term? Lydia? Negative third, yep. And then, even though we have a base of E everywhere, it's not quite ready because it has to be plain old E. It can't be multiple e's on one side. So we need to condense that using our exponent rules. If you're multiplying common bases, what are you supposed to do with the exponents? Add them. So that's just going to become e to the 2x minus 3. And your left is e to the negative x squared. So this one throws more exponent rules at you to get it condensed to just plain e to something equals e to something. Not multiple e's on the right side. Now that they're both e's, we can cross them out on both sides. And then it's also a little more complicated because they made this equation a... No, I know you're not. I know. I thought it was hilarious. Well, I didn't know what you wrote, and then when I wrote it, I was like, I died laughing. So it's a quadratic, so we got to add our x squared over. And then factor, solve. X equals negative 3, x equals 1. No, we keep going. I'm trying to think, though, if I can ever remember a case where an exponential equation had an extraneous solution. And I'm trying to decide if it's worth checking. I can't think of an extraneous. Well, I don't want you. When I'm in doubt, I'm a thorough person. When in doubt, I check. Yeah, okay. So if I do plug in 1, it'll be easier. This is going to be e to the negative first power on the left. And if I plug in 1 over here, it's going to be e squared times 1 over e to the third. Those are the same. I just plugged in 1. And so this side is just e squared over e cubed, which is e to the negative 1. So it does work. And if I plug in negative 3, negative 3 squared will be 9. And there's a negative in front of it. So that'll be e to the negative 9 on the left. Let's go check, showed that worked. And on the right, if I plug in a negative 3, power to power multiplies, so that'll be e to the negative 6 times 1 over e to the third, and then negative 6 minus 3 is, yeah, I don't think you get extraneous. Ever. So as long as you didn't make a mistake, it should check. If you should always technically still check to make sure you didn't make a mistake, but that's on you. I know when you're cute little kids, when you're cute little kids, your teachers like make you do it. Okay, so again, these are and some of them are more complicated, but these are those convenient cases. That's not real life. Real life, you're not going to get the same base on both sides. You guys did a boatload of exponential growth questions last year that are real life things when you look at trends of population and they're growing by 3% every 5 years. Don't worry, we're not going to do those. But those real life questions aren't going to have the same base on both sides. I'm just going to throw that out there. So this is very convenient to get kids to be able to wrap their head around this idea. But then realistically, you're going to have numbers to powers that don't have the same base on both sides. So, yeah. So these, you've already done. This will not be hard. These are very simple ones. These are your steps, but as soon as I talk about this, you're going to remember it from last year, although the way that people teach this can be very different. So once you get your exponential expression isolated, which in number 1 is already done, the 4 to the x is by itself, you get your variable out of the exponent by taking a log of both sides. I know Mrs. Zigai would take log base 4 of both sides. Are you Zigai? Okay. I know that that's the way she would do it. How do... You don't remember this? Okay. So then... Which works for most of the problems that you see in Algebra 2. We might get to some things here, and you'll see why, if and when we get to it, that it won't work. But it's not that much harder. I actually never used to teach it with log base 4. I just took the plain log of both sides. But here's the benefit of taking the log base 4. Yeah, sure. Here's the benefit of taking log base 4. Whatever the base is, if you take the log with that base, log base 4 of 4 to the x and log base 4 of 15, the log base 4 of 4 just cancels. That's one of your properties. So you just have x equals log base 4 of 15, and then you would just type that into your calculator. That's going to work most of the time. No, that was only 4 because that was the base of your exponent. So Ryan, this one on number 2 is going to be log base what? 3. Okay, but on number 2, we can't take it right away.
We got to add the 2 over.
Because step 1 is isolate the exponential expression. So you add your 2, you have 3 to the x equals 7, and then as Ryan said on this one, you would take log base 3 of both sides. Log base 3 of 3 cancels, leaving just x all by itself, and you get log base 3 of 7. My other way?
Yeah.
It's not going to look easier for this type of problem, but there's sometimes when it's necessary. So when I learned this, and I think it's why I taught it the way I taught it, I just took log of both sides. Because you have to remember, my calculators, this sounds terrible, I'm not that old, but my calculators didn't used to have that option that yours had where you could put in your own base. Right, it was always just log 10. So when I did it, I just had to take the plain log of both sides. I brought the exponent out in front, so it was x times the log of 4. And then you divide by log 4 on both sides. And I know Mrs. Zigai does that because I have all of her advanced PreCalc kids, and that's how they do it. So I do know a little bit more about the way she does things. But, so do you remember from last year, though, this and this are the same things. So because my calculator didn't used to have that functionality where I could plug in my base, I used to have to type in something like this, doing it this way. Log base 4 of 15 is the same thing as the log of 15 over the log of 4. That's the change of base formula that you learned last year. Do you remember that? I don't know how much you used it because your calculators don't force you to. But there is the change of base formulas, which is called the change of base formula because the calculators used to only have a base of 10. If you were doing log base 5 of 15, the change of base formula says on the calculators that I used to be restricted to, you'd have to just type in log of 15 over log of 5. It's really easy. It's just an additional thing. But kind of showing the two different methods of solving, you have like a little bit of proof as to why they're the same thing. Why the change of base formula is this into that. So, it's up to you. The three that I'm looking at right now, log base 4, log base 3, it is just a lot faster. I just had to write down a lot more work than this method. There will be some cases where, and maybe I'll get to one, that you can't use Mrs. Zigai's method necessarily. And I'll show you an example of why. But if you jump to 3, you jumped, I should take log base what of both sides? E. And log base E is the same as ln. So you'd natural log both sides. Your ln E cancels. And we're not quite done yet because there was more in our exponent than just an x. We just now have to divide by 2 on both sides, and x equals the natural log of 5 over 2. I did have an ln button, for the record, so I could just take ln. That I could do. My senior year, I graduated in 2002.
That's crazy to think you're that young.
Yeah.
Yeah, it's like I graduated in 1957.
So how many years have you been a teacher for? 4?
12.
Wait. You graduated high school in 2002?
So I graduated college in 06, so my first graduating class was 07. And this will be
2018.
this will be 09, so this might actually be my 13th. When were you born? No.
My pre-engineering science?
Yeah,
You
we were
guys-
in kindergarten.
You weren't even kindergarten. When were you born?
2001.
Oh, when you were in elementary school. You were in kindergarten. Yeah. Okay.
That's bananas.
My teacher was Mrs. Waterbury.
My teacher was a senior like 2 years ago.
Oh boy, Madeline.
Sorry.
What do I do first on 4? What? Maya.
Yeah.
Madeline is just going to be that much less prepared for her test. Aren't you proud of yourself, Maya, for jipping her of a couple points on a test? What, JR? Very good. Alyssa? Allie? Not one person in the past 2 minutes has raised their hand. I called on all of them. You would type that in. By the way, when you type it in, when you hit any log button, natural log or log, it opens a set of parentheses for you, correct? So you're going to have to close it after the 6. ln of 6, close it. Absolutely, because this one, if I don't, this one's going to take the natural log of that quotient versus this one is going to take the natural log of 6 and then divide that answer by 0.6. One's 2.3, one's 2.9. Depending on different problems, it might make a much larger difference than that seemed to, but they're different. Yeah. Let me see what the... I'm okay with this. That's fine with me. But if it says round your answer to the nearest whatever, then obviously you have to type it in. Doesn't really make a difference to me.